You. When you think of the color red, what comes to mind? Probably fire, heat, right? And blue? Ice, cold? Well, what if I told you that in the world of science, it's the complete opposite? Yeah, you heard me. Scientifically, blue is way, way hotter than red. It sounds totally backward, I know, but the science behind it is absolutely fascinating. It's just baked into our brains, isn't it? Our instincts tell us red means hot, like fire or glowing embers, and blue means cold, like ice or a deep pool of water. But here's the twist. Scientific reality flips that script entirely. When it comes to the physics of light and energy, red is actually the cooler color, and blue is the hotter one. So let's just get right to it. The answer to our big question? A resounding yes. Scientifically speaking, blue light is so much hotter than red light. I know it feels completely wrong, but stick with me for a few minutes because once you see how it works, it'll all click into place. All right, so to unravel this whole thing, we need to understand how science actually sees the color of heat. And the main clue, the secret to it all, lies in a really cool concept called a black body. It all comes down to something called black body radiation. Now, don't let the name scare you. Just imagine a perfect theoretical object that soaks up every bit of energy that hits it. When you start to heat that object up, it begins to glow. And here's the crucial part. The color of that glow changes in a very specific, very predictable pattern as it gets hotter and hotter. This is the key that connects color to temperature. Let's make this super simple. Think of a blacksmith at a forge, hammering a piece of iron. When they first heat it up, it just glows a dull red. But as they crank up the heat, watch what happens. The color shifts. It goes from red to orange, then to a bright, glowing yellow. Get it really, really hot, and it shines with a brilliant white light. And if you could pump even more heat into it, that white-hot glow would actually start to turn bluish. The lesson here is simple. More heat equals bluer light. Of course, scientists need a way to measure all this precisely. They're not just eyeballing it. And that's where a special tool comes in, the Kelvin scale. It's how they put an actual number on the color of light. So forget about Celsius or Fahrenheit for this. When we talk about the color of light, we measure it in kelvins. This is a scale of absolute temperature, which means it starts at the coldest possible point in the universe, absolute zero. It gives us a hard scientific number for the color of any light source we see. Let's look at some real-world examples to see how this works. You see a candle flame, right? With its warm, orangey glow? That's about 1850 Kelvin. That soft white light bulb in your lamp is a little hotter, around 2700 K. But then look at the light on a cloudy day. It seems kind of cool and white, doesn't it? Well, its temperature is a whopping 6500 K. And a clear blue sky? Get this. It can be anywhere from 15,000 to 27,000 Kelvin. The numbers don't lie. Bluer light has a much, much higher temperature. So, this brings us right back to that central mystery. If higher Kelvin means bluer, hotter light, why on earth do we call reddish light warm and bluish light cool? It's time to solve this psychological puzzle. So why are our brains so mixed up? Well, it's all about psychology versus physics. As one of our sources points out, our everyday cultural ideas about color, red is hot and blue is cold, are the literal opposite of the scientific facts. We're dealing with learned habits that connect colors to the feeling of warmth or cold, not the actual temperature of the light source itself. And hey, there's even a fancy name for this, the hue-heat hypothesis. It's basically the idea that our brains evolved to take shortcuts. For thousands of years, we've associated reddish yellow light with the warmth of a fire or the setting sun, and we've linked bluish light with the coolness of water or the safety of shade. It's a primal survival instinct, and it has absolutely nothing to do with physics. So here's the whole mix-up in a nutshell. When you go buy a warm light bulb, you're asking for something that gives off a reddish, yellowish light that feels psychologically cozy, but scientifically it has a lower Kelvin temperature. On the flip side, when you want a cool light for your office, you're looking for that crisp, bluish-white light that keeps you alert, and that light actually has a much higher Kelvin temperature. We're just using the language of emotion, not the language of science. Okay, so beyond being a great bit of trivia to pull out at parties, why does any of this actually matter? Well, it turns out you interact with the science of color temperature literally every single day, probably without even thinking about it. I mean, think about it. When you choose light bulbs for your house, you pick warm, low Kelvin lights for the living room to relax and cool, high Kelvin lights for the kitchen to concentrate. If you've ever taken a photo, setting the white balance is just you telling the camera the color temperature of the light in the room. Your TV, your computer monitor, they're all calibrated to a specific temperature, usually 6500 Kel, to make sure the colors look right. And for astronomers, a star's color is one of the clearest signs of its actual surface temperature. Those little blue dots in the sky, they are the absolute blowtorches of the universe. So, at the end of the day, our intuition about the world and the scientific reality don't always match up. But figuring out why they don't is half the fun, right? So, I'll leave you with this. The next time you're outside on a clear night, looking up at all those stars, the red ones, the yellow ones, the brilliant blue white ones, which of them will you now know are the